So now that we understand, we've done all the transfer function of mechanical systems, the transfer function of electrical systems, and also the transfer function of mechanical systems. Now we are going to look at the analogies of electrical, analogies that is between electrical and mechanical systems. And that is what we refer to as the electrical analogies of mechanical systems. So when you talk of analogous systems, two systems are always said to be analogous to each other if the following conditions are met. One of the conditions that we can talk about is that the first condition is that the two systems must be physically different. That is why we are talking about mechanical system and also electrical systems. The two systems must be physically different. Another one is that the differential equation modeling of these two systems are actually the same. That is when we talk about the systems to be analogous. We've said that for the systems to be analogous, two conditions must be met. The first one is that the two systems must be physically different. And then the second one is that the differential equation modeling of these particular systems must be the same. So that is what analogous system is all about. You'll find that electrical systems and mechanical systems are actually two different systems, two different physical, two different systems, and there are two types of electrical analogies of translation systems, of translation mechanical systems. And the first one, there are two. We usually have the force voltage analogy and also the force current analogy. We know that when you talk of electrical systems, then we can talk about the current force, whereby we compare the current, whereby the current represents the force. The current in electrical systems represents the force in mechanical systems, or in a situation whereby the voltage in electrical systems represent force in mechanical system. And that is now what we call how we can look at the analogous system. So we are going to start by looking at the force voltage analogy. We are going to look at the first one, which is now what we call the force voltage analogy. Force voltage analogy. The force voltage analogy. So that is the first one that we are going to look at. So for the force voltage analogy, the mathematical equation of the translation mechanical systems are compared with the mesh equations of the electrical systems. And this one we can do it by considering the translational mechanical systems that the translational mechanical system that we have. So we can have the translational mechanical system considering that part is fixed, and then from there we can have a dashpot here. We have a dashpot here. Then we have a spring K. We have a dashpot, we have a spring K, and then we have a mass. They are joined here by use of a mass M. We have a mass M, so this is spring K. And then we can talk of this one. We can call it to be B. At times it is always referred to R, but it is for the dashpot. And then a force is there, whereby we have F. And then when it is pulled, then this particular mass will move a distance x. When it is pulled, the particular mass will move a distance x. So if we look at this, the force balanced equation for this particular system, when you talk of this, the force balanced equation for this system, we can see that Fm, we can see that not really Fm, but looking at this in terms of the system, just to remind ourselves of the body diagram, then you will find that if we draw a body diagram for the same, then there will be a force that is moving it down. And if the force moves it down, the mass will be opposing, and in that case we'll have Fm, and then the spring also will be opposing, and then we can talk of F, we can call it Fk, or for the spring, and then B, which is now the dashpot, will also, the viscous or the friction will also be opposing. And therefore, for you to get the force balanced equation for this particular system, therefore we can say, considering the directions of all this, we can simply see that it is this force, and we know that it is this force that is in the opposite direction. The rest of the forces are in the same direction, and therefore we know that we have to look at the balance of forces, and in this case we can simply say that this F is equals to Fm plus Fr, or we can call it Fb, so for consistency. So plus Fb plus Fk. So that is now what it is. And therefore, if you rewrite the differential equation for this, we can simply say that F is equals to m d squared x all over dt squared. Of course, that is in time domain, plus Fr. So Fr will be R, we can talk of Fb, we can talk of Fb, b dx all over dt, and again, that is in time domain, plus kx. Again, that is also in time domain, and that is now the differential equation. We can call this one equation 1. Can call that one equation 1. So if we look at, we can now consider an electrical system of the same. So consider an electrical system that is shown. So an RLC circuit whereby we can have a V, can have that. Then we have, we can start with a resistor, RLC, R, then L, then we have the capacitor at the output. So in that case, C, and then with that, we can now have that. So in that case, now we have an electrical system. And in this case, we are talking about force voltage analogy. So if you look at this, then of course, you will find that in this case, the output is C. So if we come up with a differential equation for this, we can simply say that V is equals to the voltage that goes through the resistor is Ri, plus the voltage that goes through inductor is L di dt, L di all over dt, plus the voltage that goes through the capacitor is 1 over C integral of I dt. So that is now the differential equation. So we can substitute all the values of I, and we can call this one equation 2. Can call that one equation 2. So substituting the values of I with the dq dt in equation 2. So substituting the value of I to be equals to dq dt, substituting the value of I to be equals to dq dt in equation 2. In equation 2, if we do that, if we substitute that value, then we are going to find that V is going to be R dq all over dt plus L d squared q plus L d squared q all over dt squared plus 1 over c q plus 1 all over c q. So that is now the equation that we are going to have. We can call this one equation 3. We can call that one equation 3. So we can go ahead and compare. By comparing equation 1, the one that was relating to the mechanical system that we had, and the equation 3, that is the one that is comparing with electrical quantities, we can find the analogous quantities of the translational mechanical systems and electrical systems. And this one can be summarized by a table that we have. So you can look at the two equations. You can find that the L d squared over dt, the L d squared q over dt squared represents a second order, and therefore we can just form a table so that we can see how the systems are analogous. So we can now summarize with the two equations, equation 1 and equation 2, and equation 3, in order to come up with what the capacitor represents, what the voltage represents, and that one is now what we refer to as the analogous system. So we can have the translational mechanical system and electrical systems. We can have translational mechanical systems, this side, and again, this side, we can have electrical systems. of electrical systems. So if we look at that, remember we started by looking at the force. So in this case, the force represents a voltage V. So if you look at that, if you look at that and that, if you look at this and that, you'll find that the force represents voltage. The force represents voltage. If you look at the mass, you can go to the mass. So we have the mass here, M. So you'll find that M actually represents inductance, because you look at that, that is the second order. This is the second order. So the mass represents inductance L. So we can have force F. So force F, mass M, and inductance L represents inductance L. We can also go ahead and look at the friction coefficient B. So we can talk of friction coefficient B. Friction coefficient B, the friction coefficient B. So looking at the friction coefficient B, that one over there, and then we have it there, which means the friction coefficient B represents resistance. If you compare the two, B, that is the first order, you go to the first order in the equation 3, we have R, and therefore it represents resistance R. It represents the resistance R. Again, another that we can talk about is the spring constant K. We can talk of the spring constant K. Spring constant K. The spring constant K, so that one comes from here and that. So if you look at that, you can see Q is common, and therefore the spring constant K is the reciprocal of the capacitance. So this one is actually the reciprocal of capacitance. The reciprocal of capacitance, that is 1 over C. And then we continue and look at the displacement X. Displacement X. Displacement X. If you look at the displacement X, then this one, looking at it, X, what is common here is Q. And in that case, now the displacement X actually represent the displacement X actually represent the charge Q. So it represents the charge Q. Represent charge Q. Charge Q. Represents charge Q. So that is what we have as far as that is concerned. And then finally we can talk about the velocity V. We can talk about velocity V. So the velocity V here is actually representing what we call the current. The velocity V represents the current I. And that is as far as the translational. So when you have to look at the analogous systems of force, then force in force voltage analogy is analogous to the voltage. The mass is analogous to the inductance. The coefficient of friction is B is analogous to resistance, and so on. And that is much as in the table. So that is as far as the first analogy is concerned. There is also the torque voltage analogy, and this one's the force, the torque voltage analogy. That is now, we are now not talking about now the translational systems, but rather we are talking about the rotational, or rather the rational systems. And in that case, there is a table that you will find. So in that case, you can make a reference to EES.education, and you'll find all those tables that are going to help you, especially when we are talking about the rotational systems. So we can go to the second one under the translational systems, and that is what we call the force current analogy. The second one is the force current analogy. So the next one that we are going to look at is the force current analogy, and this is still under the translational mechanical systems and the electrical systems. So when you talk about the force current analogy, then the mathematical equations of the translational mechanical systems are compared with the nodal equations of the electrical systems. And we can consider the electrical system that is shown in the figure that is on the board. And you'll find that this circuit consists of current source, the resistor, inductor, and capacitor. And all these electrical elements are connected in parallel. So if you look at it, then in this case, the nodal equation for this will be such that I will be equals to, V over R plus, will be equals to V over R plus 1 over L V dt, 1 all over L, integral of V dt plus C dV dt, C dV all over dt, C dV dt. So those ones are actually the current. So if you look at that, then it is just a way of transforming or of expressing this in terms of current. The current that is through here will be the voltage divided by resistor. The voltage, the current that is through the inductor, we know that the voltage is L di dt. If we make the current to be the subject of the formula, then of course we are going to get 1 over L V dt, and then plus C again dV dt. So that is what we have as far as we're concerned. So in this case, we can call this one to be equation 1. So we can substitute V by, let's say, dq all over dt. Can substitute that with the dq all over dt. So in that case, we can have V substitute V with the d, substitute V with d q over dt, substitute that with the dq all over dt. And if we do that, then of course we are going to not dq but d phi, not dq but actually d phi over dt, where that is going to be the flux. We can talk of it as the magnetic flux. So in that case, we can talk of that as magnetic flux. And if we do that, then we'll find that I will now be, I will actually now be 1 over R, 1 all over R d phi over dt, 1 over R d phi over dt, all over dt plus 1 over L phi plus 1 all over L phi plus 1 over L phi plus C d squared phi over dt squared plus C d squared phi all over dt squared plus that. And in this case, we can simply say that I, and therefore we can call this one, or this one can be our equation 1, this one can be our equation 2, and we can call that, or we can just continue as this one. The other one was equation 3. We can call this one to be equation 4 because we are still going to compare. So this one we can call it equation 5. So in that case, I will now be given by C d phi. I will now be given by C d squared phi all over dt squared plus 1 over R d phi over dt, 1 all over R d phi all over dt plus 1 over L phi plus 1 all over L phi, and we can call this one to be our equation 6. We can call that one to be equation 6. And now we are going to compare. Now, comparing the equation 1, that one was for the mechanical system. The equation 1 for the mechanical system, maybe if you can remember what the equation 1 for the mechanical system was, we can talk about the equation 1 for the mechanical system. So if you can remember what it was, then maybe we can compare the two. So we can remind ourselves that F is equals to M squared d squared x all over dt squared plus B dx all over dt plus K x, if that is what we have, plus kx. So you remember this is our equation 1. So we are going to compare the equation 1 and equation, we are going to compare the equation 1 and equation 6 in order to see the analogous systems as far as this is concerned. So if we compare that, then the first thing that we will notice is that this is analogous to that. So we can have maybe translational mechanical system this side, translational mechanical systems, and then we have electrical systems. We have electrical systems. So that is now what we have. And the first thing that we can see is force F. Force F is equals to I. Force F is equals to I. We can current I, you can write it in full. Current I goes that and that. When we go to the mass M, which is the second order, mass M, if you compare the two, then the mass M is equivalent to the capacitance, C. Mass M is also equivalent to the capacitance C. The frictional coefficient B, frictional coefficient B is equivalent, looking at that, is equivalent to 1 over R, which is now actually the reciprocal of resistance. So this is equivalent to the reciprocal of resistance, which is 1 over R. It's equivalent to the reciprocal of the resistance, 1 over R. And then we can talk of the displacement. Of course, displacement. Can talk of the displacement. The displacement in this case, we are talking of x, should be equivalent, looking at that, what is changing? X and phi. Displacement x will be equivalent to the magnetic flux, phi. Equivalent to the magnetic flux, phi. And then finally, we can talk about the velocity v. Velocity v, which will now be equivalent to the voltage V. Velocity v will be equivalent to the voltage V. And that is now what the analogy is all about. You can also have the analogy for the force, not for the force now, but for the torque. Now, looking at the rotational systems. You can now look at the rotational systems, and that is now what we call the torque current analogy. And that one also you can find at the website, that is EEES.education. You can find the analogy for the torque current analogy as well as the torque voltage analogy. That is now the analogy of the rotational systems. And that is what we can have as far as the analogous systems between the electrical systems and also the mechanical systems as far as that is concerned. The reason why analogy is always very, very important is that the analogies are always very helpful in order to study and analyze non-electrical systems like mechanical systems from analogous electrical systems. So you can have a mechanical system, then from the mechanical system you can compare, you can now compare the analogy of the two systems, whereby from that you are able to analyze a mechanical system even without mechanical knowledge as far as the system is concerned. So you can just convert it to electrical systems and vice versa. Or somebody who has experience in mechanical systems can always analyze electrical systems by using that. So you'll find that making the analogies, switching from electrical systems to mechanical systems will actually be easier if you understand the analogous systems. So that is what we can do. In our next discussion, we are going to look at the transfer function of electromechanical systems, and that is the transfer function of DC motors. So that is all for now.